Hello, everyone. Today I'm going to talk about discrete signals and systems as a part of the first module of digital signal processing course. So this can be a quick recap for some of the students who have taken signals and systems before, or for other students it can be um, some concepts. If it's not clear to them, it can be useful for them as well. Okay, so let me quickly start by sharing my screen, and then afterwards I'm going to talk about um, discrete signals, and then later on the systems. Okay. And then afterwards, at some point in time, just to save the bandwidth, I'm going to uh, stop my video. Okay. And then we are going to talk about the lectures. All right. So I hope my screen is visible to you. So let me start off with from the beginning. So discrete time signals. Okay, so first we will talk about some of the basic fundamental discrete time signal. So the first one is obviously unit sample signal or a sequence. So it's a discrete time unit impulse or unit sample signal or sequence. The reason why I put sequence is just to make sure that student understands the fact that it's not a signal anymore, it's a sequence, because it's a function of n. So n is an integer value. It can take any value going from minus infinity to infinity. So unit impulse or a unit sample, commonly known as, okay. So it's delta of n. It takes the value of 1 when n is equal to 0. It takes the value of 0 when n is not equal to 0. So you have delta of n. Okay, delta of n is there, and then at a value of n is equal to 0, the value is 1. So what you do is that you take a vertical line and take a fill circle, and take a circle and then fill it. Similarly, here the value is going to be 0, so you take a circle and make it a fill circle at 0 to indicate that the value is 0. The second one is a discrete time unit step sequence or a signal. So u of n is 1 when n is greater than or equal to 0. For n less than 0, the value is going to be 0. So in other words, u of n is there. So at n greater than or equal to 0, the value is going to be 1. Okay. For n less than 0, the value is going to be 0. Okay. So just to save the bandwidth, I'm going to switch off my video. So this is how the u of n is defined. Now the question is how to express delta of n from u of n. So meaning that given u of n, how do you get delta of n? One hint I will give it to you is what happens if you shift u of n by one sample towards the right side, meaning that u of n minus 1. So that means that the origin which you see here at n is equal to 0 value would be shifted to n is equal to 1, right? So it means that this value would not be there and it will drop down to 0 for u of n minus 1. So if I subtract by u of n, okay, if I subtract, so that means that, so if I somehow subtract u of n or u of n minus 1, I should be able to get it. So let me give, so that's the hint given to you. So let me pause for a second. Let's see if you are able to find out. Okay, so what you do here is u of n is there, minus of u of n minus 1. So it means that u of n minus 1, so this point is not going to be there and it will start from 1 here onwards. So if you are subtracting, okay, with a minus sign there, so the only value you will get is at n is equal to 0, the value is going to be 1. So delta of n is nothing but u of n minus of u of n minus 1. Now the question is, how do you get u of n from delta of n? So you have this. U of n is equal to delta summation of n goes from minus infinity to n delta of n. So this we call it as a running sum of unit impulse sequence. Why we call this as a running sum is because the upper bound is decided by n, not by infinity. So now let's take an example. When n is equal to n is equal to minus 2. So u of minus 2, summation of m goes from minus infinity to minus 2, delta of m. So what would be the value? So we know that the delta of m for m goes from minus infinity to minus 2, the values are all 0. When you add all 0, the value would be 0. So here the value is 0. So when n is equal to 2, then that means that summation of m goes from minus infinity to 2, delta of m. So we know that for m going from minus infinity to minus 1, the values are 0. When m is going to have a value of 0, the value is going to be 1. When m is equal to 1 and 2, the value is going to be 0. So again, when you add across, you see a value 1. So in other words, this is now being shifted, okay, to n is equal to 2. Okay, so if it is being shifted, so that means that you are going to see when you add it, it's going to be 1 will always be there. Okay, so another way of describing the running sum is by through a change of variable. So simple change of variable can be done. M is equal to n minus k. If you put, then the summation of k goes from 0 to infinity, delta of n minus k is again it's u of n. Now if you put k is equal to 0, then u of n. So that means that u of n, meaning that you have n is equal to 0, the value is 1. Now k is equal to 1, so delta of n minus 1. So at n is equal to 1, the value is going to be 1. K is equal to 2, so again n is equal to 2, the value is going to be 1. So now you are going to add it, so it's going to be your u of n. Property of delta of n. This is a very important property. So if you have a discrete time signal x of n, you multiply by delta of n minus n naught. Let's assume that n naught is 2. So you have a x of n, delta of n minus 2. So how is delta of n minus 2 defined? At n is equal to 2, the value is going to be 1. When n is not equal to 2, the value is going to be 0. So it means that so x of n, since you are multiplying with delta of n minus n naught, or n is delta of n minus 2, then the non-zero value would only occur at x of 2, which is x of n naught. Again, for other values of n, except n is equal to 2, the values are 0. So that's why it is delta of n minus n naught. So x of 2, you have a value, and then afterwards, for other values of n, the values are 0 for x of n. Now, if you put n is equal to 0 here, so this becomes x of n, delta of n is nothing but x of 0, delta of n. Now, how do I extract the value? Meaning that x of 2, because it's still in the plot, x of 2, the value is there. For other values of n, the values are 0. So how you extract the value of x of n naught is nothing but you just take this and put a summation of n goes from minus infinity to infinity. X of n, delta of n minus n naught. So what happens to this one is clearly from this, we know that x of n naught, summation of n goes from minus infinity to infinity, delta of n minus n naught. So this value is going to be 1, because delta of n minus n naught, meaning that at n is equal to n naught, the value is going to be 1. For other values of n, the value is going to be 0. And then you add it across, so you are going to see only one value, number 1. So x of n naught. So now if you put n naught is equal to 0 here, so the summation of k goes from minus infinity to infinity, x of n, delta of n is nothing but x of 0. Then the third signal is a discrete time unit ramp sequence, which is represented by r of n is n when n is greater than or equal to 0, and 0 for n less than 0. So r of n as a function of n less than 0, the value is 0. For n greater than or equal to 0, the value is going to, as you can see, it's going to ramp up. So meaning that at n is equal to 0, the value is 0. 1, the value is 1. 2, value is 2. 3, value is 3. So on for infinity, the value is going to be infinity. R of n is nothing but n times u of n. So now, how do I write u of n in terms of r of n? Now, if you take an r of n, so what you do here is that make it of r of n plus 1, meaning that this value at n is equal to 1 will be shifted to n is equal to 0. So this value would be shifted to n is equal to 1. This value of 3 would be shifted to n is equal to 2. Then you subtract by r of n. So when you do that, the difference for a positive value of n would always be 1. So that's why it is u of n. Now, given u of n, how do you get r of n? So again, what you do here is, so what you do here is, so now the question is, given u of n, how do you get r of n? Now, so in order to do that, what you simply do here is, it's a running sum. So r of n is equal to summation of m goes from minus infinity to n minus 1 u of m. So what this means? This means is pretty straightforward in the sense that, again, what you do is that you substitute the values. How do you substitute the values? Again, n is equal to minus 3. If you put n is equal to minus 3, this is summation of m goes from minus infinity to minus 4 u of m. So minus infinity to minus 4 of u of m is going to be 0. Similarly, when you put n is equal to 3, if you put n is equal to 3, again, what happens here is summation will go from minus infinity to 2 u of m. So u of 0, u of 1, u of 2. So all each one of them has a value of 1. So that means that it's going to be 3. 1 plus 1 plus 1. So it's going to be 3. So you're going to get the 3. Now again, if you do a change of variable, which you can do, summation, when you do m is equal to n minus k, so summation of, then summation in this case would be changed to k is equal to 1 to infinity u of n minus k. Again, same logic apply. N is equal to k is equal to 1. So that means that at n is equal to 0 is being shifted to n is equal to 1 for u of n minus 1. Okay, so that means that at n is equal to 0, the value is going to be 0. Now, u of n minus 2, u of n minus 3, you do that and then add it across. Once you add it across, then what you are going to get again is going to be r of n here. Now, one important point, why it is not 0. Why it is not 0 is just to make sure that at n is equal to 0, r of 0 is 0. Okay. So to summarize, what we have done so far is, if from, so u of n you can get from r of n through a running sum. So running sum of delta of n would give you u of n. Running sum of u of n would give you r of n. But notice that the upper bound here is n minus 1 for r of n with respect to u of n. There it is, upper bound is n. Okay, for this one. Okay, which is there in the notes. Okay, now if you want to get from r of n, you can get u of n by simply using this expression. You can get delta of n from u of n by making sure that u of n minus of u of n minus 1, if you do that. Okay, any questions? Okay, let me go further and we will talk about signum sequence. Signum sequence is defined by SGN of n, where for n greater than 0, it takes the value of 1. For n is equal to 0, it takes the value 0. For n less than 0, it takes the value of minus 1, which you can see it. Signum of n as a function of m, the value is going to be 1. For a positive value of n is equal to 0, the value is going to be 0. For negative value, it is again minus 1. So the fifth elementary signal is the discrete time complex exponential sequence. This is nothing but x of n is equal to e to the power of j omega n. Why do we talk about e to the power of j omega n, complex exponential sequence? Because this acts as a basis function for computing discrete time Fourier transform as well as inverse discrete Fourier transform. If this omega is discretized, then we are talking about discrete Fourier transform and inverse discrete Fourier transform. So now, let's talk about complex exponential sequence. X of n is equal to e to the power of j omega n, where some of the properties are it has infinite total energy and finite power. So I hope you know the definition of how to compute the total energy uh, and the power in the sequence. So if you do that, then it's gonna be an infinite total energy and finite power. So that means that it's a power signal. Any periodic signal is a power signal. Okay. So now omega naught, if I take one specific omega naught, and if I make it and if I add it by 2 pi, so meaning that omega naught is equal to omega naught plus 2 pi, then if I go here e to the power of j omega naught plus 2 pi n, this is nothing but e to the power of j omega naught n multiplied by e to the power of j 2 pi n, where n is an integer, right? This n is an integer. So this is gonna be 1 throughout. So this is going to be e to the power of j omega naught n. So what this is telling me is there is no distinct value of omega naught. Omega naught, after some interval of 2 pi, it is going to be the same omega naught. So omega naught is equal to omega naught plus or minus 2 pi m, where m is an integer. So no distinct value of omega naught. Now, this is a very important aspect in terms of discrete sequences, discrete signals, because or a complex exponential or a discrete time complex exponential sequence. Because if you look at a continuous time complex exponential sequence, e to the power of j omega, t can take any value going from minus infinity to infinity, correct? So considering that part, there will not be any, so there will always be a distinct value of omega naught. So because in the continuous there will be a there, so the omega naught which you will compute will be a distinct value. So that means that you cannot, after some point in time, you will not get the same omega naught. This will only happen because of the fact that e to the power of j omega n, where your n is an integer. That is why you will have no distinct value of omega naught. Omega naught will repeat after some time. What is after some time is nothing but plus or minus 2 pi m. Because of that, the frequency length has to be 2 pi. So in terms of the when we compute discrete Fourier transform, okay, or when we look at discrete time Fourier transform, we predominantly look for a frequency length of 2 pi, omega naught going from 0 to 2 pi, where 0 is inclusive, or sometimes we go from omega naught from minus pi to pi, where minus pi is inclusive. Sometimes what we do is that we go from 0, that's a rare scenario, omega naught going from 0 to 2 pi with 2 pi inclusive, or omega naught going from minus pi to pi inclusive in this case. Okay. Why this is required is because this forms a basis function. This is the general formula for discrete time Fourier transform. This is a general formula for inverse discrete time Fourier transform, which you know from your signals and systems. Now, very important point here, the length of the frequency, the range for omega is minus pi to pi. There is a frequency length of 2 pi. This is a very important aspect. When you compute the inverse continuous time Fourier transform, look at your notes back, you can see that it is integration minus infinity to infinity. Okay, so that is a very important aspect. Now I'm going to talk about periodicity. Okay, periodicity by definition is x of n should be equal to x of n plus capital N. Correct. So where n is capital N is period. Okay, n capital N must be greater than 0 and it must be a integer. The smallest n is nothing but my fundamental period. Okay. So let me stop the video just to save the bandwidth. Okay. Now I am going to go back to the same logic of trying to see for the complex exponential sequence what is the periodicity. So we know x of n is equal to e to the power of j omega naught n. So I put e to the power of j omega naught n, which is the same. Now I replace by n plus capital N, e to the power of j omega naught n plus capital N. So this is going to be e to the power of j omega naught n multiplied by e to the power of j omega naught n. When this side would be equal to this side, provided only when this is going to be 1, right? So when this is going to be 1, when this is going to be 1 is only when omega naught n capital N is 2 pi m, where m is an integer. So this brings up to a very important concept of periodicity. Omega naught divided by 2 pi should be m times capital N, which is nothing but a rational number. Remember that both n and m and n has to be integer and both should be greater than 0. So otherwise it's going to be a aperiodic signal. So basic definition which we have proved here is to determine whether the signal is periodic or not, we look at omega naught divided by 2 pi has to be m times capital N and it has to be a rational number. This apply for a sinusoidal signal, like for example sine of omega naught n, cos of omega naught n as well. Okay. Now so this n is my period. N is going to be, if I substitute here, simplify here, this becomes 2 pi m divided by omega naught. When is this going to be a fundamental period? This is where the students do get confused with period and the fundamental period. So this is a very important statement which I have written. For a period n to be a fundamental period, for period m, which is here, to be a fundamental period, little m has to be a smallest integer such that it makes capital N an integer. So that means that I need to identify the smallest integer value of m such that my capital N becomes the integer. Okay. Once I have my fundamental period, then the fundamental frequency can be obtained by 2 pi by capital M. Now let me go through some of the examples here so that you will have an idea about what I am talking. Okay. So x of n is equal to cos of 8 pi by 31n. So now I want to determine whether the signal is periodic. If it is periodic, determine its fundamental period. Since it's a cos signal, obviously it's a periodic signal. So what we do here is omega divided by 2 pi. What is my omega here? This is cos of omega n. So omega is nothing but 8 pi by 31. 8 pi by 31 multiplied by 2 pi. This is 4 by 31. So this is a rational number, m by n. So n is equal to 31. Make sure that this is in simplified form. Okay. So this is n is equal to 31. Now, let me help you out in terms of what is the significance of this, why m has to be smallest m. Okay, so if I go back to the definition here, same definition, n is equal to 2 pi divided by omega naught times m, which is written here. So 2 pi omega naught is 8 pi by 31, which is this, times m. So this is 31 by 4 times m. Okay. So what should be the value of m, smallest integer value of m, such that my capital N is becomes the fundamental period. So here, because this is 4 is there, so m has to be a positive, m has to be greater than 0. So this has to be positive 4. So that means that m has to be 4, then n is going to be 31, which is shown in the example here. Now, what happens if I take n is equal to 8? What happens if I take n is equal to 12, 16, so on? Then if I take that, still it is going to give me an n, which is an integer, but it is not going to be a fundamental period. It will be only be a period. That is the difference between the two particular aspects. Okay. Now, let me take another example here. It's a combination of the two signals. X of n is equal to e to the power of j 2 pi by 3 times m plus e to the power of j 3 pi by 4m. So again, you do the same thing, omega 1. So this is because there are two signals, so that's why I put omega 1 divided by 2 pi. This is nothing but 2 pi by 3 times 2 pi. This becomes 1/3. This is a simplified form, n1 is equal to 3. Similarly, omega 2 divided by 2 pi. This is nothing but 3 pi by 4 times 2 pi. This is 3 by 8. N2 is equal to 8. This is going to be, now, since individually this is a fundamental period of 3, this is a fundamental period of 8. But since it's being added or subtracted, then you have to take a LCM. So LCM of 3 comma 8, as we know that it is going to be 24. So what is your fundamental frequency? Fundamental frequency is nothing but 2 pi by capital N. Capital N here is 24. So this is pi by 12. So now, what I am writing here, so in this question, again, it was the same thing, determine the fundamental period as well as the fundamental frequency. Now, I went one step forward and just wanted to put it in terms of the harmonics of the fundamental frequency. So the k, so by fundamental, so x of n, this is e to the power of j 2 pi by 3 n. Now I'm putting in terms of e to the power of j 8 pi by 12. So pi by 12 is nothing but your omega naught. So this is of the form of e to the power of j k omega naught n. So this, in this case, the k is nothing but k omega naught. So this is nothing but the harmonic of the fundamental frequency. So here the k is 8. Similarly, here the k is 9. So what we call this as, this is the 8th harmonic component, and this is the 9th harmonic component of the fundamental frequency. Okay. If you have any questions, anything, you are more than welcome to put it in the chat box. Okay. All right. Now, so far what we have done is we have discussed about yeah. So far what we have done is we have discussed about discrete signals. Okay, discrete signals. We have spoken about discrete signals, basic discrete signals like delta of n, u of n, r of n, signum. Okay, signum function. And then we spoke about the complex exponential sequence, the periodicity. Okay, uh, uh, and what is the significance of the fundamental period? What is the significance of little m with respect to capital N? Okay, so these are the some of the basic things which I wanted to make sure that I convey to the students. Now I'm going to talk about another important aspect, which is called as a system, because what happens is from a digital signal processing perspective, so what we have is we have a signal can be anything. Okay, and then but the system is also there. The system is the one which we want to design and make sure that we get the desired output. Okay, so there are some properties which we talk about the systems as well, and then afterwards we'll look into some of the other examples associated with it. Okay, right? Let us go back to the my notes again. So let me talk about discrete time systems. Okay, now as I said just now, you have an x of n is there. It is passed through a discrete time system. You get an output. Okay. So again, let me just okay. All right. So the system can be in a different form. One, you can have a cascade system. So two systems put together in cascade. So your input is x of n, output is y of n. The another one is a parallel system. So meaning that x of n is there, you have the same common input going. In this case, it's x of n. You get S1 and S2. These are the two subsystems, and then it is passed through a adder, and then finally you get an output. You can have a combination of these two, meaning that cascade parallel combination. The, the fourth one, which we predominantly talk in control system, is the feedback system. Okay, so that means that output in some form feedbacks to the input. Okay, now system properties. What are the properties associated with the system? That is the one which we are going to discuss today. Okay, system properties. So whether the system has memory or memoryless system. In other words, memory meaning the dynamic, memoryless is static. Whether it's a causal system, linear system, time invariant system, stable system, or invertible system. Okay. Now let's start with the proper definition associated with it. When do we say the system is memoryless? So output, which is y of n at a given point at or a given time. Uh, Let me take it back. When do we call a system as a memory system, memoryless system? Output, which is y of n at n is equal to n naught, depends upon the input x of n only at n is equal to n naught. Otherwise, we call it as a memory system. So best way to do here is just substitute the value of n. So at n is equal to 0, this is x square of 0. So so n is equal to 0, so n naught is equal to 0. Correct? So this is nothing but it's a memoryless system. But this is a memory system. Why? Is because at n is equal to 0, it depends upon x of 1. So it depends upon the future value of your input signal. Okay, and now it's not just putting one values of n. I usually recommend you to put multiple values of n so that we will have a better idea of what is happening. Okay, so if value is -1, so this is n is equal to -1, this is going to be 2. Again, y of -1 depends of x of 2, again the future value. Okay, now if I put y is equal to 3, then this is x of -2. It depends upon the previous or the past values of the input. So this is going to be a memory system. What is a causal system? Causal system output y of n at n is equal to n naught depends on the input x of n for n less than or equal to n naught. So no future values. So the output at n is equal to n naught depends upon the input value. So there are three possible scenarios. Depends upon the input value at n is equal to n naught, or it depends upon the previous values, which is n less than n naught, or it depends upon present and the previous value, which is n less than or equal to n naught. Three different cases will pop up, but make sure that it should not have a future value. Now here n is equal to 0, x of -1. So it depends upon the previous value. Okay, so that means that this is a causal system. Now n is equal to 2. Here this becomes n is equal to x of 3. So it means that it is depending upon the future value. So it's a non-causal system. Okay. Third one is a linear system. Linear system, what I have felt is some of the times students have difficulty understanding the linear system. Let me go in a little bit of more depth to make sure that students do understand this particular concept. Linear system meaning that a linearly combined input produces a linearly combined output. Okay, so what is this mean? So for that, what we have to understand is that linearly combined inputs. Linearly combined inputs meaning that I need to have two inputs. Let's assume that the input is x1 and another input is x2. So x1 of n produces y1 of n. x2 of n produces y2 of n. So the linearly combined input meaning that ax1 of n plus bx2 of n, which is nothing but x3 of n, should produce linearly combined output, which is a y1 of n plus b y2 of n. This is going to be y3 of n. So it means that if I give x3 of n, I should get y3 of n. What is x3 of n? x3 of n is a linearly combined input. In other words, it's ax1 of n plus bx2 of n. What is linearly combined output, which is y3? y3 should be a y1 of n plus b y2 of n. Okay, now let's take a very simple example. Is a squaring operator a linear function? Clearly, we know that the squaring operator is not a linear function. So y of n is equal to x square of n is the first. So what does the system actually do? System is actually, the input is your x of n. The system is nothing but it is squaring it and giving you the output y of n. So again, x1 of n produces y1 of n. So first thing what you do is that y1, so wherever you see x, y, put y1. Wherever you see x, you put x1. So y1 of n is equal to x1 square of n. Similarly, y2 also you do. y2 of n produces y2 of n is equal to y2 square of n. Similarly, x3 of n should produce y3 of n. So which is so y3 of n, which is nothing but x3 square of n. What is x3 square of n? Is nothing but ax1 plus bx2 whole square. So what happens to this? This is nothing but this is a plus b whole square. So this is not going to be equal to, so this is not equal to a y1 of n plus b y2 of n. What is y1? Is nothing but in this expression, this is a x1 square of n plus b x2 square of n. So this is not going to be a linear operator. Okay. Now, the second last one, because we had to talk about the two more important properties. Time invariant system. What does invariant means by English dictionary? Invariant meaning that the time invariant. Okay, let me put in the time also. Time invariant. The system that doesn't depends upon the time. Okay, so meaning that if x of n produces y of n, then x of n minus n naught should produce y of n minus n naught. Clear? So it means that if the input, if a system is there, if I present an input x of n, if I get an output y of n, if I shift the input by some amount, the output should be shifted by the same amount, provided the system is invariant system. Okay, so there is a simple test for whether the system is time invariant or variant. So what we do here is we take a signal x of n, we pass through a system, we get y of n. Then we shift the output by some factor, let's assume n naught. So then this becomes y of n minus n. Now the same shift, we pass it to the input signal x of n, shift, then you get x of n minus n naught, then you pass it to the same system. Then I'm putting a dummy expression which is y of n naught n, you get an output. If both the outputs are same, then it is a time invariant system, meaning that it does not depend upon the time. So that means that the shift here becomes irrelevant. Okay, in other words. So let's look at some of the important properties, because again here we feel that students do get confused with this particular aspect. x of an plus b. This is a very important concept. Any operation done on n will make the system time variant except a is equal to 1. Again, any operation done on n will make the system time variant except for a is equal to 1. So let's look at this scenario. Y of n naught is equal to x of minus n is this. This is given. Now the first thing which you need to understand is the input is your x of n. What is the system doing? System is making sure that the signal is time reversal. Okay. So first thing is that y of n minus n naught. Y of n minus n naught, wherever you see n, replaced by n minus n naught. So this becomes x of minus n plus n naught. Correct. Now you shift the input. Remember this. Now you're shifting the input. Minus n here is coming because of the time reversal. So y of n naught n is nothing but x of minus n naught. Not same. So that's why it is called as a time variant system. Okay. So time invariant, in other words, the input output characteristic should not change with time. Stable system. Okay. All right, my bad. There are two other properties as well. Okay. Stable system. Stable system, there is a very important term which is called as a BIBO, which is a bounded input, bounded output. Bounded input meaning that x of n, if you take a magnitude value, should be less than or equal to some value b1. That value should be less than infinity for all values of n, produces a bounded output, which is y of n magnitude should be less than or equal to b2, should be less than infinity. So remember that b1 and b2 are some finite constant value. So the important aspect here is the bounded output should produce a bounded input for all values of n. Okay, this is where again students do get confused. They just look at some values of n and then they don't do for other values of n, and they find out that it's a stable system or a unstable system. Okay. All right, or a stable system or unstable, whatever it is. But what you need to do it is you need to try to look for all the my bad excuse me. So for all values of n, including n is equal to minus infinity and infinity. So students do make a mistake, meaning that they look at some finite values of n, they don't look at infinite values of n, which is minus infinity to infinity. So just be careful while making this specific observation to determine whether it's a stable system or not. Okay. So let's take this example. Y of n is equal to summation of k goes from minus infinity to n u of k. Okay. So what is your input here? There is no x, but it is input is in the form of an elementary signal, which happens to be u of n. Is u of n bounded? Answer is yes, because at n greater than or equal to 0, the value is going to be 1. N less than 0, the value is going to be 0. So either it will be either 1 or 0. Okay. So now the input is bounded. But what is the system doing? Some system is doing a running sum, which is nothing but summation of k goes from minus infinity to n. So the output is going to be unstable. Why? So now, if you look at a positive value, some value n is equal to 2. So what will happen for n is equal to 2? So you will get y of 2 is going to be 3. Okay, y of 4 is going to be 5, for example, because we are going to add up. So if you look at only positive finite values of n, then you are going to say it as a stable. But you have to always remember that it can hit for all values of n, meaning that it also includes minus infinity to minus infinity as well as infinity. But now when n goes to infinity, obviously it shoots up to infinity. So its y of n is going to be unstable. So in these cases, you need to identify a specific value of n such the system becomes unstable. And we cannot say that for this specific range of n, the system is stable, and this and for this specific range of n, the system is unstable. We cannot say that. If the system is unstable, so it is unstable throughout. Y of n, another example, y of n is equal to n plus 1 u of n. Okay. So why it is going to be unstable? So the input is u of n, but the system is multiplying n plus 1. So at n goes to infinity, u of n goes to infinity. So it's going to be unstable system. But even though u of n is bounded system, bounded input. Now, if I change the u of n to x of n, so n plus 1 u of n. So if the system is x of n is there, it's not a part of some basic definition of the elementary signal like u of n. If x of n is there, then you end up, now here you have to assume that the input is bounded. So you can argue that why, sir? The point here is very important concept is that you will not pass an unstable signal or an unstable input to a system, because there is no point in doing that. So here you will assume that x of n is bounded input. Okay, you will assume that x of n is bounded, but still because of n plus 1 n there, it is going to be an unstable system. Now y of n is equal to x of 3n plus 1. Y of n is equal to x of 3n plus 1. So input is bounded, meaning that x of n magnitude is less than infinity. If this is input is bounded, if you shift, if you scale, the y-axis values are not going to change. In terms of the y-axis value, the range is not going to change. So the output will still be bounded. So it's going to be a stable system. But whether it's a time variant or invariant system, it is going to be a, what is the value a here? If you go back, because of the scaling operator, a is 3. So it is going to be a time variant system. Okay. Last but not the least, invertible system. A system is invertible if we can determine its input x of n uniquely from its output. So x of n is there, you get an output y of n. Okay, and then from y of n you want to get your x of n back. Okay, uniquely. So that means that x of n is there, you pass through one system, so you get y of n, you take y of n, passes through another system, then you should get x of n back. So if that happens, then the S1 is called as an invertible system, S2 is called as an inverse system. Now, another important point to be you should remember while thinking about invertible system is your x of n should be uniquely determined from your y of n. So one simple test to determine whether the system is invertible or non-invertible is, say for example, if you give if two input produces the same output, like for example 4 and minus 4 produces the same output. If this is a squaring operator, 16 and 16, so you cannot determine x of n uniquely, so it's not going to be an invertible system. So in that particular aspect you need to look at it whether it's an invertible or a non-invertible system. Again, x of n should be uniquely determined from, should be uniquely be obtained from your output y of n. Okay, so the test for the invertible system is if the two inputs produces the same output, clearly it's a non-invertible system, because obviously you cannot retrieve your original input signal x of n uniquely. Okay. All right. I hope this was useful for you. Let me stop at this point. Let me show. I hope this was useful for you. Thank you very much.